Okay, in this lecture video, we're going to talk about the structure of atoms and what they're made out of. So, first of all, the smallest piece of an element that you can have and still have that particular element is an atom. Check. Then when you have atoms of different elements, they're going to have different properties. So they're going to be made of different things. And the atoms of any particular element can have different masses or charges and still be that element. So for example, I could have two samples of the element oxygen, and they could have different masses from one another. Each atom within those two different samples could be different in their mass. They could also have different charges. So I could have one atom of oxygen that has no charge, and another atom of oxygen that might have a negative charge, but it's still oxygen. So you can have atoms of the same element that combine with each other and they still have that element. For example, hydrogen gas. So you recognize hydrogen off the periodic table, I'm sure, right? It has the symbol H. But we never find hydrogen atoms floating around the atmosphere by themselves. So hydrogen is always found as a pair with two hydrogen atoms linked together. But it's still an element. It just has more than one atom composing that element. But the atoms are the same. On the other hand, if you have atoms that are different and they combine together, then you form compounds. So for example, we have water, which everyone knows what water is. You drink it every day. And then we have hydrogen peroxide, which has two hydrogens and two oxygens, as opposed to water, which only has one oxygen. So when you form compounds, the ratio of the atoms, in this case hydrogen and oxygen, always come together in the same way. So that means hydrogen always has two hydrogens and one oxygen. We don't show the one. And hydrogen peroxide, on the other hand, always has two hydrogens and two oxygens. There's a really good joke you might have seen where it says a guy walks into a bar and he says, "Oh, I'll have a glass of water." And then his friend's like, "Oh, that sounds really good. I'll have an H2O too." And so he dies because H2O2 is hydrogen peroxide. That's the stuff you bleach your hair with. So the point is that if you change what these subscripts are, when you have hydrogen and oxygen together, you change the identity of that compound. So water is always H2O, and hydrogen peroxide is H2O2. So this may seem like a very small detail, but it's actually quite important. Now, sometimes you can have elements or compounds that then interact with one another to form new substances, and we call this a chemical reaction. But during this chemical reaction to form new substances, it's important to remember that you're not destroying what you started with and making something brand new. You're just taking the atoms that you already have and you're regrouping them into something else. So a good example of this is a common way that we get energy in our daily lives, and that's from the burning of sugar. So the chemical formula for sugar is C6H12O6. And our bodies burn sugar, so we burn it off. You've heard that, right? We burn off our energy, we burn our fuel. Well, when we burn things, it really means that we're reacting with oxygen. So if you combine sugar with oxygen, the atoms in those molecules regroup to instead form carbon dioxide and water. So you know then we breathe out the carbon dioxide and we get water in lots of different ways. But if you were to go and add up all the different types of atoms in these molecules, you would find that on this side of the arrow, where we're doing the chemical reaction, what we're starting with, you'll find 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. And if you come down to this side of the equation to see what our new substances are, carbon dioxide and water, you will again find 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. And don't worry if you can't see that right now. We're going to go over chemical reactions and how you write formulas and how you count up the atoms later on in the semester. But for now, it's just important to note that we didn't create or destroy atoms. We just regrouped them to form new molecules. So in order to understand how these chemical reactions happen, we have to look at what these atoms are made of. And they're made from 3 subatomic particles. So on this side of our table here, we have the types of subatomic particles. Let's go through each one. So the first one is the proton. Its symbol is P+, and the reason why we put that plus there is because each proton has a charge of +1. And then you can see here that it's mass, and we're measuring mass in kilograms, which is what the rest of the world uses to measure mass, although we're used to measuring mass, or really I should say weight, in pounds. So that might be a more familiar number to you, pounds. So the mass of a proton is very, very tiny, times 10 to the minus 27. So that means if I was going to write this number out, its mass, I would write it out as 0 point, and then I would have to write 0, 0, 0, 0, dot, dot, dot. I would have to write a total of 26 zeros, and then the rest of the number, 1673. That's how many kilograms it would be. So that's a really, really tiny number. If you wanted to know how many pounds that was so you could compare with your bathroom scale, then that would be the equivalent of about 4 times 10 to the minus 27 pounds. So really, really a tiny number. Then we can check our next subatomic particle. Let's look at neutrons next. So neutrons are represented by an N0, and sometimes that 0 is written as a subscript, depending on how I'm going. And that 0 is there because neutrons have 0 charge. So they are neither positive nor negative. But they also have about the same mass as a proton. So very, very, very tiny. Our last subatomic particle then is the electron, written as the symbol E minus, because electrons have a negative charge, a charge of -1. But what's really interesting about electrons is if you look at their mass, now we're looking at 10 to the minus 31 kilograms. So that mass is so tiny. It's even tinier than protons and neutrons. But it's so tiny that when you're looking at the mass of a single atom, we don't even count the mass of the electron. So it's so much more tiny than even the protons and the neutrons that its contribution to the overall mass of an atom overall is insignificant. So let's take a look then at how these particles are arranged, these subatomic particles in the atom structure. So in this case, let's put our nucleus in blue, and inside this nucleus, that's where our protons and our neutrons can be found. So our protons are in there and our neutrons are in there. And then the electrons are located in an electron cloud. And I'm representing this electron cloud as just a bunch of yellow squiggles. So this electron cloud is pretty amorphous, right? And within this cloud, the electrons could be anywhere at any given time. And really, there's a lot of empty space located in this electron cloud. So when we talk about where the electrons are, they're outside of the nucleus. So they're outside of it. And they're located somewhere in this cloud, but we can't pinpoint exactly where they're at, and we can't say exactly how they're moving, but we can get some information about them, and we'll talk about that a little bit later. Just to put it to scale for you, if the atom was the size of a football stadium, then the nucleus that has all the mass, remember the protons and the neutrons are the only thing that contribute to the mass, the nucleus would be the size of a grape in the middle of the 50-yard line, okay? And then that electron cloud that we were drawing earlier would take up the rest of the entire stadium. And actually it would go down into the ground, right? Because the nucleus is in the middle. You got to think of the stadium as a sphere that surrounds that 50-yard line center point. So the nucleus is a grape. That grape is too big. I can't draw a tiny enough dot with my stylus here on my iPad. But the grape is at the center of the 50-yard line, and the electrons are located somewhere within the rest of the stadium. So that's just to sort of put it to scale if we were to make atoms as big enough that we could actually see them. So let's sort of look at how the subatomic particles compare for elements or for atoms of different types of elements. The first thing to note is that when you have different elements, they have different numbers of protons. So if you change the number of protons, you change the identity of that particular element. And that's what happens with radioactivity. So the nuclear bomb, things like that, those all come from converting one element to another by changing the number of protons in the atom. The second thing to remember is that you can have atoms of the same element that have different numbers of neutrons. So since neutrons contribute to the mass of an atom, if you change the number of neutrons, you change the mass of the atom. So we mentioned that at the beginning of the lecture video. So you get different masses of atoms of the same element by differing the number of neutrons. And these atoms with different masses are called isotopes. So for example, you may have heard of carbon-12 or carbon-14. So carbon-12 is plain old carbon. That's 95% or something of all the carbon in the world. Carbon-13 is an isotope of carbon with a different number of neutrons that's used in different medical applications. Carbon-14 is another isotope of carbon that's used for radioactive dating. That's how we find out, how old the Egyptian pyramids are. So all of these atoms of carbon have the same number of protons and electrons, but they have different numbers of neutrons. So in carbon-12, there are 6 neutrons. In carbon-13, there are 7. And in carbon-14, there are 8. But they're still all forms of carbon. So lastly, we can have atoms of the same element that can gain or lose electrons. So now you still have the same element, but now you have an ion, and that ion has some sort of charge associated with it. So these atoms of the same element, they still have the same number of protons and the same number of neutrons. So if you have the regular atom, the number of protons and the number of electrons are the same. So that means overall you have 0 charge. The positive charged protons cancel out with the negatively charged electrons. But if you have a case where your atom loses electrons, now you're looking at a situation where the number of protons that you have is greater than the number of electrons that you have. And if that's the case, you now have more positively charged particles in your particle, or in your atom, than you have negatively charged particles in your atom. And if this is the case, you have a positively charged ion of that atom, and we call it a cation. So cations are atoms that have lost electrons and now have more protons present. On the other hand, you could have an atom that gains electrons. And in this case now, the number of protons that you have in that atom is less than the number of electrons. So that means the amount of positive charge that you have in the nucleus is less than the amount of negative charge that surrounds it in the electron cloud. So now you have an ion that has an overall negative charge, and that ion is called an anion. So cations and anions are still the same atom of whatever atom they came from, but now they're no longer neutral. They have either a positive or a negative charge.